Yeah, so what I would like to talk about today is why neural networks have so many parameters or need so many parameters. It is not a complete explanation, but it's at least suggestive. It shows basically that, well, you will see. It proves that if you want to basically have low loss, then you have to have a lot of parameters. And the meat of this is joint work with, oops, sorry about that, with Nikhil Ghosh. And there I will also discuss joint work with Li Kuei. Okay, so let me sort of start by, you look at the neural networks, right, and the architectures, and, the obvious thing is that these things are very complex, right? And sort of a theorist, we would like to understand what is the role of this complexity. You can think, well, okay, there are many units here, and it kind of seems a little bit, the architecture seems a little baroque, right? So if you think about it, it's, kind of reminds you of this. If you have kids, you probably have seen it. This, oops, I'm sorry. Getting used to the remote. So, this is the house moving castle, and it certainly moves, right? But it's probably not the most efficient way of transportation, and it looks very complex. So can we somehow understand the aspects of neural networks in a little simpler? What we have seen in recent years is like one very striking aspect of this, is that the neural networks just keep growing in size. So this is a summary for 2017. The size of each circle here corresponds to the number of parameters for architectures from a small ones, which about 5 million, to big, those big circles with 150 million. And what we see is that, like this was 6 years ago. 6 years ago, there were architectures with about 150 million parameters. And in fact, the first one that I showed you is actually one of the small ones. It has about only 5 or 6 million parameters. So, of course, that was 2017, and they just keep growing, right? So GPT-3 had 175 billion parameters, right? This is to scale. And now they're even bigger. There is something called switch transformer, which has 1.6 trillion parameters. So you can, like those circles are here. You can try looking for them. So what's going on? Like, why? And this is definitely a very, very systematic thing. There is a nice summary from a recent paper from DeepMind for a bunch of these architectures. And we can see that they're all in like 100 billion and higher. So between 100 billion and a trillion, a little like half a trillion, but there are even bigger ones. And they are being trained on data sets whose size is kind of similar order, about between 100 billion and a trillion. What's going on? So why so many parameters? Why so much complexity? And I'll try to sort of give at least one story of what's going on. And so let me set it up. So as usual, we will have data, x, y, yi. And my data xi are features in RD, and yi minus 1, 1 for classification. Actually, I'll primarily consider regression today. And under standard statistical assumptions, when the data sampled IID, the best predictor that best generalizes to new data, right? That's the point. Take this training data and generalize to data we haven't seen. The best one is simply the one which minimizes the loss function over the full probability distribution of the data. Of course, we don't know the probability distribution because by definition it's unseen. So, what we do in practice in what's called empirical risk minimization, we minimize over some class of functions over the training data. And one of the sort of key aspects of machine learning is this tension, because what we're minimizing is the empirical risk, and what we want is the expected risk. And sort of if you think about the standard generalization bounds, they're saying that, well, empirical risk and the expected risk should be close together. If I can somehow control capacity and they're close together, then it's good. Right? I can prove stuff. But what we have seen is that in practice, they're not actually that close together. So there is this idea of interpolation. It's probably familiar, but let me just sort of go over it quickly. Is that you can drive the empirical risk to zero, and it is still okay. So classically, like we've said, well, a model with zero training error overfits, right? And actually, I like this one from Yorfi, Kohler, Krzyzak, and Wok. And they have this picture, and they say that, so this is an interpolating curve, and this is somehow non-interpolating predictor. And they say, well, the estimate on the right seems to be more reasonable than the estimate on the left, which interpolates the data. It's kind of an interesting, right? It's like reasonable, right? It's what does reasonable exactly mean? Certainly it looks more reasonable, right? But what is reasonable? Okay, in any case, as we have seen in practice, this is not really the case. You can train neural networks to have 100% accuracy, and you don't see much overfitting. And in fact, it's not a new thing. And boosting the margin by Shapir, Freund, Bartlett, and Lee, that was in '98, they actually said that in boosting, the test error of the generated hypothesis usually doesn't increase as its size becomes very large and often is observed to decrease even after the training error reaches zero. So this was not even a new observation, although it somehow didn't completely register, I suppose. What we see in practice is something like this. We see that, so this is for a kernel machine, so I can actually compute exact solution. And this is the green dashed line is the exact solution, the test error of the exact solution. And this line, the solid line, is what happens on test when I train it by stochastic gradient descent. So what we see is that it somehow keeps decreasing with the number of epochs and sort of just converges to the exact solution, and it never kind of goes up again, like what standard theory would suggest. On train, what we see is that, of course, interpolation train error is zero. It's numerically zero, 10 to the minus 27. And what we see is that, my stochastic gradient descent just keeps going down, exactly the way we would expect. Now, so there are 2 points here to be made. First point, of course, is that I can just solve this problem exactly, and I don't need stochastic gradient descent. I just get zero loss on my training data, and it works fine. It works as well as the best predictor. On the other hand, here is an interesting thing. You can see that after 10 epochs, my training error is actually 10 to the minus 4, which is very far from 10 to the minus 27. But I'm already doing as well as I'm ever going to do. So from a practical point of view, there is really no reason to have accuracy higher than 10 to the minus 3 or 10 to the minus 4, right? That's the early stopping point. So in practice, we don't actually achieve interpolation, and I'll discuss this. And we don't even care whether it interpolates or not. Okay. So yeah, I really like this quote from Ruslan's tutorial that basically say, like, if you want to build a good system, you basically have to be able to interpolate. And this is not the end of it, but if you just do this, if you just drive the error to zero, you already usually get a pretty reasonable result. Okay, now, so here is a kind of first intuitive explanation of what happens with interpolation. And this is, in some sense, I think, I presume that most of you have some intuition about interpolation, but if you don't, this is probably the kind of right intuition to think about. And the easiest way to think about it in terms of the Shepard's interpolation. And the Shepard's interpolation is simply the following scheme. You just take inverse distance, what's called inverse distance kernels, just 1 over x minus xi. And to build a predictor, you take f of x to be sum yi k of xix divided by sum of k xix. And this is what's called a Nadaraya-Watson scheme. Now, there is an easy claim to prove that this is really an interpolation. So f of x equal, that should be xi. F of xi is equal to yi. So this goes to infinity, but both denominator and the numerator go to infinity, so they cancel out. Easy to check that this works out correctly. So this is kind of an interpolation. And it turns out, and this was actually, I believe, Shepard's master's thesis at MIT. And it turns out, and this was a remarkable result by Devroy, Georg, and Kurajak, that what they call a Hilbert scheme, which is exactly that, with some power alpha equals d, when d is a dimension, is that this thing is consistent for regression. Now, this is actually, I think, quite a remarkable result, because as you can see, there are no parameters here other than dimension. You just get it for free. So you just get consistency. It's some sort of universal consistency result. If you are willing to have parameters, you can do a little bit better. You can actually prove that it's not just consistent, but it has optimal rates, and it has many other nice statistical properties. And this was the joint work we did with Daniel Supar-Dimitri, and then a follow-up with Sasha Raklin and Sasha Tsibakov. And basically, you know, the intuition is something like this. So this, I think this kind of picture is maybe the mental picture that is useful to have if you don't have that. So let me describe this picture, and then I kind of go back to that. And so what is this picture? You have a very simple model. It is simply y equals x plus noise, okay? And of course, the best predictor for such a model for regression, right? So this is how my data sampled, all these little data points. And of course, the optimal predictor for this is just simply the line y equals x. And if you simply do linear regression, you will find that it's okay. Or you will find something close to it. But now, if you use one of those schemes, you get this red line, or red curve. And the red curve has this very interesting property that at no data point, it is particularly close to the blue line, right? So it's actually very far from the blue line at every data point. And yet, if you somehow look away from your data points, it's actually not that far from the blue line. So it's a good approximation for the blue line on average, but it's not a good approximation for blue line at any data point. And this, I think, is a very sort of non-traditional kind of predictor. And essentially, this is a mental picture for what deep learning does. And I'll give some evidence for this, but this is what was called benign overfitting or harmless interpolation. And basically, there have been a lot of theoretical work showing that this picture is somehow typical. Something like that is really happening. There is a nice survey in particular by Bartlett, Montanari, and Raklin from last year. Oh, no, it's not last year anymore. It's 2 years ago. Now, we also did some work with Adit Radhakrishnan and Caroline Euler. And in fact, what you can show is that sufficiently deep neural network under some settings exactly do this. So it's not just a mental picture, it's actually exact in a certain sense. So that's maybe the sort of mental picture, but now it's still, even with this, it's still not completely clear why so many parameters are necessary for this. Like, this doesn't explain the number of parameters at all. And sort of to maybe give some intuition about the number of parameters, it's useful to look at the double descent curve. And what you observe here is that for P, so P here is the number of parameters, and then is the number of data points. So in the classical regime, P is much less than N, and you sort of have this kind of traditional predictors. In this modern regime, when P is much bigger than N, you have curves like this. So that's maybe the mental picture. And what do you expect, of course? Well, if you take this curve seriously, then you realize that you have to go sufficiently to the right, because going to the right actually decreases your test error, right? So this curve suggests that you should be sufficiently overparameterized if you want to be in the modern regime, in the interpolating regime. Of course, this curve doesn't tell you that you have to be, because you have solutions here which may be just as good, right? In some cases better. But if you want to be there, then you better be kind of away from the peak. So that's maybe the first intuition. And so very large models perform better than just simply large models, but not necessarily better than small models. So that's the first sort of intuition about this. Now, one thing, and this is a little bit of an aside, but it's kind of, I think, interesting if you are into such things. You can view this as a certain sort of, you can think about two limits, right? One limit is your number of parameters goes to infinity. Another limit is the number of data points goes to infinity. And classically, what do? Like, you increase the number of data points and slowly increase the number of parameters with the number of data points, right? Like, you're controlling VC dimension or some measure of complexity of your system. And basically, N is much, much smaller than P. And if N is bigger than P, I'm sorry, the other way around. P is much smaller than N. And of course, if P is comparable to N, you overfit. So if you think about what happens, to be optimal, you need P grow much slower than N. So N goes to infinity first, and then P goes to infinity, sort of. If you do it the other way around, you get overfitting. And of course, these are not the same. If you look at this modern picture, the one I showed you, it's actually kind of saying that going this way or that way, you roughly get the same. So you don't get the same predictor, but you get the same performance, more or less. So that's maybe like one intuition, is that somehow this modern machine learning somehow gives you this commutative diagram. Okay, that's an aside. So if you're not into commutative diagrams, let me now show some mathematical result, basically saying what happens. What can we actually show? And let me first start with result by Hosmel, a very nice result in ICLR 2021. And what he showed is the following. Well, before I explain, let me just do a setup. So suppose I have some feature map from RD to RP. Okay, an arbitrary feature map. You need it to be non-degenerate, but other than that, it's arbitrary. And suppose now I have the following model. Y is simply equals to W star times f phi of x plus some noise, and the variance of the noise is sigma squared. Okay, that's all. Now I'm going to suppress this phi because this phi doesn't do really anything, so I'll just write x instead of phi of x, but it works for random models, random feature models, and all sorts of other things like that. Now, assume now that the square loss of my predictor is equal to 0, okay? So this is interpolation. This is exactly interpolation condition. Then what he showed is the following, that expected value over my training data of Wn, so that's my prediction that I obtained from data, x minus y squared, so that's the square loss of my predictor, minus the square loss of the optimal predictor, is bigger than sigma squared n divided by p plus 1 minus n. So let me unpack this. So first, n is the number of data points, remember, and p is the number of parameters. And so what is this quantity? This quantity is simply expected excess loss, right? So the best possible predictor is just if I somehow, if an oracle tells me what W star is, right? That's the best. And for that, this will be 0. For everything else, this will be worse than 0. Or this will be, I mean, bigger than 0, positive number. So if I have a very good predictor, right, it better be that this quantity is small. Now, what does this inequality tell me? This inequality tells me that this quality cannot be small, assuming sigma squared is non-zero. So let's just think of sigma squared being 1 to be like specific, so I don't have to worry about it. Of course, if there is no noise, then this disappears. If sigma is equal to 0, then this is not saying anything. But suppose sigma is equal to 1, so there is some label noise. And now this is saying that this quantity cannot be small unless p is much bigger than n. Okay? And what does it mean that p is much bigger than n? That means that I am significantly over-parameterized. So if I want this to be like, 0.1, then it better be that p is roughly on the order of 11n, right? So I need 11 times as many parameters as the number of data points. So let me kind of go over this, and then I'll say why this is not completely satisfactory and give a more general result along the same direction. So first, some observations. And, oh yeah, I should point out, I'm not assuming anything here, right? I'm not assuming anything about the model. I'm just assuming my data ID. I'm not assuming, oops, sorry. I'm not assuming, the only thing which is I'm assuming is that my variance is point-wise bounded from below. That's the only non-trivial assumption. Everything else is trivial. And I think I probably need some moment to exist. But yeah, so it's very, very general. It's remarkably general result. Now, consider general bound. So this is a very general bound, right? It's distribution independent. It's okay. So in his paper, actually, it was specifically for pseudo inverse, so minimum norm regression, but actually that turns out to be unnecessary. In any case, so consider now this and consider exact formula for the Gaussian, which from our paper with Daniel Su and Mark Zhu. And it turns out that the general bound almost exactly matches the bound for the Gaussian. So it's really quite remarkable, right? Because this is an explicit analysis, because for the Gaussian, you can just work out those things. And this is some sort of general bound, which is even distribution independent, and yet it matches almost exactly. I think it's quite amazing. Now, first point is that p bigger than n is necessary for small excess loss, right? Under interpolation. Excess loss becomes infinite for p equals n. So actually, for the Gaussian case, it becomes exactly infinite for even finite p equals n. In this case, you can only do it when n and p go to infinity, otherwise it's finite. But okay, it still will be very large, right? When p is equal to n, this is 1, and this is n. So the lower bound will be n, which is huge. And finally, this is suggestive, but doesn't fully explain practice, right? Because it doesn't match practice. And why doesn't it match practice? Why doesn't it match practice? Well, it doesn't match practice because I assume exact interpolation. And in practice, as we just discussed, nobody does exact interpolation. At least it's not commonly done. Right? You usually do some sort of early stopping. And you stop at points which don't interpolate. So let me now kind of go one step back and let's look at practice. And this a bunch of data set. And this is from our paper with SlowDNN. And these results, these green results, are actually optimal. And what do I mean by optimal? We take the optimal parameter. Well, okay, I don't know whether the parameters are optimal, but whatever they chose in those papers, so presumably they tuned them and so on. So it's hard. Of course, we don't know that they're optimal, but it's hard to get much better much better results with these architectures at least. So it's a realistic setup. And what you see is the following. You see very consistently that the test error, say 30% here, the train error is 4%, right? 5%, 0.7%, 9%, 0.8%, and so on. So yes, first, train error is definitely not 0, but it is at least 10 times, roughly 10 times smaller than the test error. So you clearly training them, it's clearly a very non-classical setup, but it is still far from interpolation as such. So you can do more of this experiment, you roughly see the same thing. It's very consistent. There are a few data sets for which they actually are close, but it's like 2 data sets out of 20. So the majority of data sets, the training error is much smaller than the test error. Okay, so how would we analyze this? And the main result is that it's a double descent actually is universal even when we train below, even when we allow early stopping or any regularization method. And let me explain what this means. So I'm taking exactly the same model as before and the same assumption as before, but now I am changing the condition slightly. So before, remember, I was assumed that the loss was 0. Now I'm saying that the square loss is not 0, but it is below the noise level. And why does it have to be below the noise level? Well, you see, if I just plug in the optimal, suppose an oracle tells me that, okay, W star is the optimal predictor. Then if you plug W star here, then there is no training, right? It's just W star. If you train W star here, you will see that the loss of the optimal predictor is exactly equal to the noise level, right? So if I want to exclude the oracle, right? Because otherwise there is always a method which just gives me the oracle. Somebody gives me the oracle, right? I have divine inspiration, I plug it in and I get the result. So that's, I want to exclude this. So how do I exclude it? Well, I have to say that I'm training below the noise level. And so instead of sigma squared, I need some sort of tau sigma squared, and tau has to be smaller than 1. That's what training below the noise level means. And arguably what we have seen is that in practice, people almost always train below the noise level. Okay. This, as you can view, as some sort of normalized loss. And when tau is equal to 1, then of course you can just plug the optimal one. So now here is a theorem, and this is joint work with Nikhil Ghosh, and the whole discussion which I will have from now is joint work with him. He really did an amazing job analyzing this. So here is a result. So suppose you have any probability distribution, and suppose you have any algorithm. It really doesn't matter what algorithm you use. So it's completely universal bound, almost completely universal. The only thing, I'm just assuming that my algorithm gives me output which is below the noise level. It's below tau. That's my only constraint. Now, how you get it, I don't care. You can do early stopping. You can do regularization. You can do any sort of different ways in which people get this. Or you can do exact interpolation. Yeah, Renee. No, it's not in the denominator.
So why?
Give me 1 second. I don't think I can tell you exactly why, but I can give you a comparison with the So think about, oh yeah, let me point out, for interpolation, tau would be exactly 0, right? Tau equals 0 is interpolation. So this is a relaxed version of interpolation. And think about tau being equal to 0.5. So think about it significantly lower than the noise level, but much higher than 0. Yeah.
In the product of W and
Oh, I
X.
just suppressed phi because it's annoying to write it always. You can just put it everywhere.
I see, but when you have this, in the product, you mean you are in the product thing with phi, right?
With phi.
Phi of X.
It's just, phi doesn't really do anything and it doesn't change anything. The only thing for phi is to being non-degenerate.
I see, I see.
That's why I'm suppressing it.
Thank you.
Yeah, technically I should put phi everywhere. Okay. So, oops. Okay, so this is the claim. So the excess loss, just as before, is equal, greater than sigma squared n over p, 1 minus square root of tau squared. Okay? And now I'm going to sort of unfold this. Sorry. Okay. So first, remember the result I just discussed of Hausmuller? That's for tau equals 0. Now, I can plug tau equals 0 here, of course, right? I just put tau equals 0. And what do I have if tau equals 0? I just have n over p sigma squared. And here I have sigma squared n over p minus n plus 1. Not quite the same thing, but very similar, essentially the same, as long as p is significantly bigger than n. Okay? Oh, by the way, this bound also works when p is smaller than n. That one I think doesn't. But in any case, think about p being bigger than n, then n over p and n over p minus n is about the same thing. The difference is small. So it almost matches for tau equals 0, so that's nice. Now, notice that if I stop short of interpolation, right, let's think about what does stop shorting of interpolation mean? Well, tau is equal to 0.5, as I said before. If tau is equal to 0.5, then, a simple calculation with a calculator tells you that 1 minus square root of 0.5 squared is about 0.7. So you get 0.7 there, which is, a very benign factor. So essentially 0.5, doing full interpolation and doing 0.5, which is very far from interpolation, gives you almost the same bound. The factor is just 0.7. And finally, as I mentioned before, p smaller than n is also fine. Notice that if you have, this actually tells you something quite interesting if p is smaller than n, right? Because if n is bigger than p, right, you want this thing to be small. Well, how can it be small if n is bigger than p? The only way it has to be small is that this thing has to be small, right? To compensate, because if n is bigger than p, then n over p is bigger than 1. So it better be that this is a lot smaller than 1. How can this be a lot smaller than 1? This can only be smaller than 1 if tau is very close to 1. So this says that in the traditional regime, interpolation is not possible. This actually pushes you away. If you want to have accurate bound in the classical regime, you have to be very far from interpolation. Okay, so that's basically that. Now, you can do something a little bit more precise. Well, actually, it's a lot more precise. And this is a so-called Barchenko-Pasteur setting. So assume that everything is, just assume everything is Gaussian and the distribution is Gaussian. So I'm jumping from any distribution to this very specific thing when you have this random matrices of Gaussian random matrices essentially. Well, they don't technically have to be Gaussian, but yeah, I would rather not go there, the condition. But I'll just think about Gaussian. And I'm also taking the limit. So before everything was non-asymptotic. Now it has to be asymptotic. N and p go together to infinity. N over p equals to some gamma. Okay, there is some fraction. Then you can prove the following theorem. We prove the following, is that for small tau, the lower bound becomes this very, it's much more specific form. It's sigma squared n over p minus n times 1 minus tau to the 1/2 square root of p over p minus n, okay? So notice here what happens when p is much bigger than n. This is essentially n over p. This becomes 1, right? And I'm just getting my previous bound. So it matches. Again, very nice because this analysis uses completely different technology from the other one. It uses random matrix theory. It only applies under these conditions. The previous analysis applies under any condition. There is essentially no. It's almost completely general. So you can see that the general bound is tight when gamma is sufficiently bigger than 1. Basically, when gamma is much bigger than 1, it's tight. You can, in fact, see that. Like you can numerically see that the things match pretty well. Interestingly enough, you can also look at the interpolation. So this gives you, so let me go back to the previous bound. And you see that around the interpolation peak, this tells, sorry. Around the interpolation peak, right? What happens at the interpolation peak? N is equals to P. And this bound doesn't tell you very much, right? It just tells you that, like, if tau is bigger than 0.5, this tells you that, assume sigma is equal to 1. This just tells you that the generalization loss is bigger than 0.7, which is kind of not very strong because you actually expect it to be infinite. So nicely for the Marchenko-Pasteur setting, you can, in fact, prove this. And the bound is actually quite nice. So when gamma is close to 1, sorry, I'm struggling with this pointer. When gamma is close to 1, you can have the following. The bound becomes sigma squared, 1 over 4 tau, plus tau over 4 minus 1/2. So it's very precise. And here is the interesting thing. So notice how sensitive it is to tau. So if I'm driving tau to 0, so when tau is 0, this is interpolation, this is exact fit. This actually goes to infinity, and it goes to infinity, it has a pole, right? The polar for the 1 at tau equals 0. But if tau is just a little bit bigger than 0, this almost completely disappears. So it's very easy to smooth the peak. And in fact, I believe that probably was the reason it happened so much, not just in the past, is because you actually, even small regularization will remove this, right? Add a little bit of regularizer, right? Just a tiny bit, like 0.1, and that already makes it much, much smaller. So the peak is extremely sensitive to tau, to the degree at which you deviate from interpolation. But look now at the tail. Whether tau is 0 or tau is 0.1 essentially makes no difference at all. So the universality of this comes through the tail, not through the peak. The peak is really very sensitive, but the tail is almost completely robust. Like you actually, the only way to remove the tail is to drive tau all the way to 1. That's the only way. And that, of course, will just drive you to the classical regime when you're very far from interpolation. So I think there is this kind of interesting, sharp distinction between what happens in the peak when you do regularization and what happens at the tail. And arguably, the tail is what's interesting, right? Because that's where we want to be. We want this bound to be small, right? We don't want it to be big. Who cares? I mean, the peak is kind of cool. It's like this sharp thing. But who cares? So that's basically the upshot. If interpolation peak is very sensitive, while the tail is extremely robust. And this is kind of what you have, 1 over tau versus 1 minus square root of tau squared, right? Completely different dependence. Okay, so let's see. So actually I'll summarize and I'm happy to take questions. I think I'm well ahead of time. So, summary. First, if you want to train below the noise level, you have to overparameterize, at least for these linear models. There is no other way. So either you train at the noise level or you don't overparameterize. Yeah. For the linear feature case, yes. Well, presumably it should also be true for nonlinear, but it's hard to prove. Yeah. It's so that's kind of interesting, right? You have this. It's almost like you either don't overparameterize and then you're in the classical regime, and then you have to train at the noise level, or you overparameterize and you train below the noise level, and then you need a lot of parameters. And it looks like modern models are almost always trained below the noise level. I'm not actually proving that this is necessary or optimal, but it seems to be an empirical fact. And if you take that fact as a given, and you sort of agree that this is a reasonable model for that, then you have to be overparameterized. Significantly overparameterized. Now, the peak of double descent is sensitive to early stopping regularization, while the tail is robust. And again, this doesn't depend on the nature of the algorithm or nature of regularization you have. If you want to have a good algorithm, you always have to do it this way. This is a universal bound for all algorithms in all regularization methods. Interesting parallel with this work by Bubek and Selke recently, when they showed, in fact, this was kind of partially inspired by their work on, they showed that overparameterization is necessary for robustness in terms of the Lipschitz norm. This is what we're showing, is that it's necessary for generalization. I think it's a very different setup, but it does somehow feel that this overparameterization allows you to do things nicely somehow. And finally, for nonlinear families, I presume it must be true as well. Well, it seems much harder to prove. Certainly, these methods don't really apply to sort of non-feature-based model directly, but there may be other ways to do it. It seems to be true, but I mean, I would argue that sort of historically we have seen that linear models are actually pretty insightful as far as nonlinear models are concerned, but you know, that remains to be proven. Yeah, I'll stop here and I'm happy to ask questions. Happy to take questions, that is.
Great talk, Misha. So you mostly talk about lower bounds. So under what regimes do you have matching upper bounds with these lower bounds?
Excellent question. So we don't have a matching upper. So I don't know. I don't know. It's a really good question, and it needs to be like, we actually have to work this out. Because, oh yeah, this, I forgot to say one more thing about this. If you want to have some rate, you know, like in non-parametric statistics, they usually want to have some rate, right? It's like n to the, you know, like 3 over d or something, some function of d. So you can actually plug here the rate, and then you see that essentially, if you want to get rate, the degree of overparameterization actually has to match that rate. So you can do this, you can play this game asymptotically, and you will see how much overparameterization you need to play to get this rate. But it doesn't show that the rate is achievable. It just shows that this is the least that you need to have it.
So I was wondering for the, you said that deep neural network is essentially implementing the Shepard's interpolation, did you mean like Nadaraya-Watson kind of interpolation, or is there some other interpolation scheme using the Shepard's kernel? And also, I guess another like very related question is like, for this almost interpolation tau, is it still like a Shepard's kernel, or maybe a less sharp kernel would do? So I was hoping to get your thoughts on that.
Yes, so for classification, it exactly under some, so you have to set it up correctly, but yes, you can prove that it's exactly Shepard's, the Nadaraya-Watson using Shepard's. Oh, I'm emphasizing what I've done here was for regression, that is for classification. And the reason is for classification, you can ignore denominators. But it's exactly Nadaraya-Watson with a singular kernel, and you can analyze everything there in terms of your activation function. What happens, but that is for exact interpolation. I don't know what happened there if you have some sort of regularization. So it's a sort of orthogonal story to this one. I haven't really discussed that.
So are there equivalent results for logistic regression? With,
what? Sorry.
Yes, sure. I was just wondering, are there like equivalent bounds for logistic regression with log loss?
Can you say it a little louder, please?
Okay, it's not working? Okay, sorry. So I'm just wondering, are there equivalent bounds for logistic regression with cross-entropy loss?
Logistic regression. I don't know. Yeah, the analysis relies on the square loss. Presumably it should be the same, but I don't think the analysis will work in this form. You would need a different technique.
Okay.
I mean, it would be very, okay, I should say, it would be very surprising to me if it would be significantly different, but I don't have a proof.
Okay, thanks.
Hi. Yeah, here. Thank you for the interesting talk. Just a question regarding overparameterization, right? So in linear regression, linear models, achieving, like there is a unique way to achieve parameterization, sorry, by increasing the number of parameters, right? But in a deep neural network, for example, we can increase the width or increase the depth. So my question is, do you observe, at least empirically, similar like double descents by, for example, fixing the width and increasing depth, or fixing depth and increasing the width, etc.? Thank you.
Yeah, so I think depth and width are very different. So I think a good, maybe a good intuition for this is to think about increasing depth, increasing width is somehow making things more smooth, somehow you're averaging it out. Increasing depth seems to make, if you think about it in terms of the kernel, it seems to make this kernel sharper. Well, actually, it doesn't seem, you can prove it in some settings, it actually makes the kernel sharper. So if you're using, you know, like your kernel becomes kind of larger and larger.
I mean, you mean like the NTK or something?
Yeah, so think about the NTK regime. You have a kernel, so if your depth goes to infinity, your kernel becomes unbounded. It becomes singular kernel, and you actually get Shepard's interpolation scheme.
I see. Thanks.
Hi, Misha. A very nice talk. I'm not sure I fully understood the statement that double descent is universal. So, I mean, the lower bound implies the first bullet that you wrote here, that overparameterization is necessary. So when you say that double descent is universal, do you mean the same thing in other words, or you mean something a little bit different?
What I think, what I mean by universal is that if you look at the tail is not really algorithm dependent. If you just think about it as a lower bound, if you think about it the following form, I mean, you can think about it in many ways, but think about it just saying like, if I want to have a good model, I have to have a lot of parameters, or I have to have very few parameters. That, I think, is a universal thing, and that you cannot get away. So what these bounds show, right, that the tail is super robust. like whatever you do with your algorithm, you are not getting away from the need to have like go way, way in the overparameterized regime. So in that sense, it's universal. The peak on its own is not universal unless you require like strict interpolation. The peak depends on the exact interpolation.
Mm-hmm. Okay.
That's
Thanks.
I wanted to go back to the last question. Your last bullet point is about nonlinear models. And there, as the previous to the last question argued, you have depth and width. But I think the real question is, what's going to be the x-axis of these double descent plots?
yeah, so my feeling is you have to look at the widths, right? You somehow fix the depth. Because if you allow depth go to infinity too, I don't know. Well, so if you allow width go to infinity first, and then depth go to infinity, I think the story will still be fine. If you somehow like make them go to infinity at the same time, I really don't know what's going to happen. I don't have any intuition.
But more generally, is really what about the invariances that exists when you have deep networks, right? There'll be transformations that reduce the number of effective parameters, and therefore how to measure the x-axis is unclear.
Yeah, so this is a really good question. In fact, you can, okay, I'm sort of arguing against myself here, but let me, this is really annoying. Sorry, I don't know how to go all the way to the first slide. Okay, thank you for the patience. So look at this. You see that the number of parameters here and the number of training tokens is actually about the same. You may say, well, aren't we at the peak of the curve? Maybe it's not overparameterized. And one possibility actually is that it may be, this is not doing regression, right? This is doing classification. And it may be that a lot of the tokens are very strongly correlated and somehow effective dimensionality. There are like a bunch of invariances and equivalences and whatnot, right? And it may be that even though it looks like it's 300, 300 billion tokens, but maybe it's like effectively like 10 billion. I don't know. I'm just putting random numbers there. But it does look like they're probably far fewer than you would expect. So it may be that, so presumably invariances will shift you on this curve. But I don't think we have like any understanding what exactly is happening. This seems to be like crucial, right? To, like the real thing.
Hello, I have a question about this noise level. So in results which you show, the parameter tau was very important because there is a non-trivial dependence on it, and so so important is how close we to interpolation level. And to answer this, we need to compare with the noise level. But so when in the setting where we control the noise level, when we set it ourselves, it's easy. But what if we don't know the noise level and we do some experiments? So is there some principal way to determine noise level which we have in some experiments which we do?
Yeah, so that's a good question. How do we know the noise level? And oops, I keep missing this. Sorry, where did I have my table? Yeah, so look at this. We don't know the noise level, but what do we know? We do know that the test and train are quite different. And if we think that these networks do a good job, we should expect that the test is not too different from the noise level, right? So, okay, it's obviously not perfect. So if it says 9%, maybe like the best predictor would be like 5%. But it's very hard to imagine that the best predictor would be 0.1%. So I think taking the test error as some sort of rough estimate of the noise level, you know, give it a fudge factor, give it a factor of 3, okay? So maybe it's like 3% at least. But this is 0.9, right? So we're still way below the noise level. This is, of course, you know, hand wavy, but I think it's a pretty reasonable when we're dealing with actual like, data like that.
Thank you. Can I have also one more for about noise level? So in this regression setting, it's so what's noise level? It's clear because we have this Gaussian noise or any other random noise. But what if we have some, some task like CFR? We can treat it as a regression, but without noise. So in this case, technically there is no noise, but it's. But we still need some noise level.
In fact, these are classification results, so you can say, okay, I'm kind of cheating here. Fair point. I still think this, like just looking at this and taking this to be the noise level, up to some like factor of 2 or 3 is still pretty reasonable. So I kind of feel, okay, we only have proof for regression, but I sort of feel that you can take the same and kind of translate it to other loss functions. And you probably should have something similar. Yeah, this remains to be proved, but I think.
Thank you.
Yeah,
Okay, maybe we can
Misha,
take last question.
You mentioned Marchenko Pastura, and I remember that a couple of years ago we made an observation, and later found out it was well known, that for linear problems, the condition number has also a double descent.
Right.
Exactly in the same parameters.
Right, because it becomes,
So the question is, you mentioned generalization, you mentioned Lipschitz robustness, there is also the condition number. Are all those things related? How do you think about it?
So somehow the condition number comes in directly, right? Because when you're fitting noise, your basically matrix becomes poorly conditioned at that point, right? As you know. I don't. So in some sense, there is some sort of. Okay, there is some mathematical phenomenon, right? Square matrices tend to be badly conditioned. Like, sorry, that's how it is, right? We teach about square matrices, which is a worst case in some sense. I mean, but this is a little unsatisfactory from. So there is some sort of fundamental mathematical thing about square matrices.
Yeah, and stability.
This relates directly to stability, right? And presumably directly relates to the Lipschitz condition. That's exactly what you would expect.
And to generalization.
Yeah. So I think in some sense, the fact that conditioning and relates to all of the things is, at least post factum, it's not surprising.
I'm sorry, so I don't think we have enough time for more questions. Okay, last one.
Sorry, this one will be quick. So you're kind of comparing with models with at most p parameters, and like you're saying there's a lower bound. Can you kind of like extend this to like models with like low norm instead of like having like possibly with infinite width or something, like with infinite number of parameters, but like have a bound on the norm and like compare to the best possible predictor with that bounded norm constraint and like have a lower bound, if that makes sense.
Well, no norm would be kind of like a type of regularization, right? So I think you just need to rewrite no norm in terms of your training loss. So, which is kind of similar, right? Because your training loss cannot be the training loss and the norm are related. So if you can write one in terms of the other, you can directly plug it in, because this doesn't assume any algorithm. So whatever you do with the norm, as long as you can write it in terms of tau, it will work.
Okay, I see. Thank you.
Thanks so much for this great talk.